Our next presenter is supposed to be Dr. Zhen from China, because also the travel restriction, and he cannot be here. Professor Suranja Shah will present this. Professor Suranja Shah from the University of Austin, Arlington. And his presentation today is the effect and mechanism of carbon nanotube on the early age hydration performance of cement-based materials. Please join me to welcome Professor Suranja Shah.
I guarantee you that I would not be presenting anything in the second session. So because all the people are there, yeah. So Zhen Li, she did her postdoc with me and David Core when I was at Northwestern. She was then at Dalian Institute of Technology, and now, as you can see, she is teaching at Harbin Institute of Technology, which is, considered one of the very good university in China. But Harbin is, Zhen Li tell me, it's even colder than Chicago, but it's way north. So, but she could make it, as Kejin mentioned, because of COVID. So there is so I'm going to give you an introduction and the experimental program she did, some results and a discussion, and the conclusion. So I think there are many applications, transportation and other things, where we need certainly high compressive strength, small porosity, as well as the simple production process. And one of the issue that we are studying is the early hydration, and I think many of you are familiar with various stages such as induction, acceleration, and stable period. And what happens in early hydration obviously can have a profound effect on later on. So what Zhen Li studies is, in the first up to about 24 hours, what happens in hydration. And her emphasis was whether CNT can, how does it influence hydration? It's less studied than many other properties. People have shown that addition of small amount of well-dispersed carbon nanotube has substantial, significant improvement in many properties, such as tensile strength, Young modulus, transport property. But as I mentioned, Zhen Li wanted to study what happens of CNT during very early hydration. But just to show you the example of what CNT can do on the hardened property, so here some work done that Professor Consta and I have done using very small amount of CNT, carbon nanotube. These are 0.1% and very well dispersed. There was a discussion of dispersion in the last presentation. And so you can see, so we have results of unreinforced, that is without any 0.1, and with 0.1% CNT or carbon nanofiber. And so this is without any small addition of CNT, and this, and this is, so you can see that as far as the flexural strength, it's almost double, and also maintaining the fracture toughness, which is also important in many applications. Similarly, not similarly, but we also observe that not only the mechanical, but some transport property related aspects are substantially and improved. For example, here for very low water to cement ratio, we have shown the autogenous shrinkage, and you can see the amount of CNT here is 0.048%. So it's rather really small. And so this is autogenous shrinkage. That is the shrinkage when there is no drying shrinkage during early part of curing, it's substantially reduced with autogenous shrinkage. So these are, and there are other examples. For example, some work done with, again, Professor Consta and his group is I had already mentioned it in the previous talk, the increase in piezoresistivity. And you can see that with addition of the CNT, we can increase the piezoresistivity as shown here. So the experimental program that Zhen used is shown here, and you can see that we use same amount of superplasticizer and water to cement ratio, but different amount of carbon nanotube from 0 to 0.5%, and the property of CNT we used are shown in the top slide. And as I had mentioned earlier, it's very important, and the dispersion process. So here, as shown here, that we start with the water, with the superplasticizer, and then with CNT, and then it's ultrasonicated. In this case, she did it for an hour. So for that particular energy, we had realized that 1 hour is just about ideal. And then rotary mixer, and then she tested for isothermal calorimeter and other tests, 1 hour, 3 hour, 7 hour, and 24 hours. And as you can, it's shown here, the curing condition. Now, this, too bad Jan is gone, but this was the question I had asked Jan. So I had, initially, if you look at it, well, you say there is really not that much difference as far as the results from isothermal calorimeter. And if you look at the time shift, it's less than an hour. That is a bit, let's say 0.3%. It is smaller than control by, I think, less than an hour, which is only few percent. And we didn't do any TGA. So apparently, based on other results, this could be important, that there is an influence of the hydration shown also in the cumulative curve. We don't understand why 0.1% is lower than the control, but that's what we observed as far as the cumulative curve is concerned. So then she studied at the FTIR results, as I mentioned, at different hours and with a different addition of carbon nanotubes. So here, the FTIR results of unhydrated cement clinker are shown with hydrated at different time, 1 hour, 3 hours, up to 24 hours. And I guess you can see from here that with hydration, the calcium hydroxide, the peak representing OH, shows that there is formation of crystalline calcium hydroxide crystal. But let me double check that I'm doing the right thing, the number of hours. So this one is 1 hour, 3 hours, 7 hours, and 9 hours, but it's not clear here. Oh, sorry, I shouldn't do that. Oh, sorry. But I wanted to show you with CNT. Okay, this is 1 hour, but with a different amount of CNT. And I think main conclusion, even with different hours, there are no new peak. So there are no new hydration product. But there are one thing that, well, you will see increase in at the peak corresponding to OH. But one thing I wanted to point out, and that I showed it before, that the frequency at around 500 with the addition of CNT increases. And that means that there is a more polymerization when we have CNT as far as the tetrahedron is concerned. And this I had shown it earlier, but it at the wrong place because there are no CNT. But we had observed that this peak is moved, the frequency is increased when we have CNT, and I come back to that later on. As far as the importance of this is concerned. Then I want to skip to the results of X-ray XRD curve. Again, there are no new peaks, so addition of CNT doesn't really change the hydration product. But very important, she observed, and here I've shown here the calcium hydroxide crystal orientation is reduced when you have CNT. And that means that the size of calcium hydroxide crystal is smaller when we have CNT. So there are two observations that I thought were important to point out. One is that with CNT there is a more polymerization of CSH, and also the calcium hydroxide crystal size is reduced. So I want to show you what, then the SEM observation, and you can see that the porosity, the material is more dense, so porosity is reduced. We did not measure, as Jan had done very well, the pore structure using MIP or other methods, but you can, from here it's clear. We can also see that the size of the calcium hydroxide crystal, as I mentioned earlier from the XRD, is lower when you have CNT. So I want to, here is also the CSH needle type without, and then you can see three-dimensional dense CSH when you have carbon nanotube. So, so if I conclude, the main point, as I mentioned, is that the addition of CNT can improve the rate of hydration, and also, as I mentioned, the increase in polymerization and decrease in size of the calcium hydroxide crystal. So I want to, so those are the increase in polymerization and decrease in size of the calcium hydroxide. So those are the main conclusions from the study on XRD, SEM, and isothermal calorimeter. So what are the, based on this, I want to show what are the supporting observations and what are the, what is important. So we have observed, not in this study, but I thought it's interesting to add, that we measure using ESCM in CSH when you have 0.1% carbon nanotube and when you don't, and plotted here is calcium to silica ratio. So you can see that the calcium to silica ratio decreases when you have CNT. And that obviously collaborates also the increase in polymerization. Then we also noticed that because of we did the work on nano indentation. Again, nano indentation with the CSH where you had, when you had CNT and when you don't, and you can see that the curve has moved to the right, so that the material with CNT is more denser. And this results at the nanoscale are collaborated with the larger scale work. So this is the measurement from notched beam test, measuring the modulus of elasticity. So you can see that when we have addition of CNT, for example, at 28 days, the modulus is increased as much as 85%. So these observations that we made on early age hydration or increased polymerization and reducing the size of crystal has implication in mechanical property. Now, what happened earlier, the work done at Purdue University with titanium dioxide, they showed that titanium dioxide also reduces size of calcium hydroxide crystal. And they observed as a result of that, if you do the CO2 curing, there is more accelerated. So we were very curious, and we had noticed in other work, not with CNT but with graphene oxide, that the size of calcium hydroxide crystal. So we decided to do the CO2 curing with 0.1% GO and without GO, and you can see the results of CO2 sequestration. You can see there is a substantial increase, 30%, when you have, I think, what's the amount of GO here? 0.5% and 1%. And not only that, but the mechanical properties are addition of GO for both uncarbonated and carbonated is substantially increased. So it's very interesting how the observation at the scale we made at the nanoscale collaborated very well with the other properties. So I think that I will conclude with that.